are live. Okay, so we're starting with this warm-up here. Thinking back to grade 11, unit 1. 1/2 to the power of n, if n is going to be 0, then 1, then 2, then 3. Basically every whole number from 0 to infinity. If I added up all of those terms, what should I get? Who remembers doing that stuff back in grade 11? Do you remember what we called it, first of all? I have a hand up. What did we call this stuff? This is, very good. You remember, somebody remembers September. That's good to hear. This is what we would call an infinite geometric series. If you're adding it up, you call it a series. Otherwise, you could just call it a sequence. But I did say I wanted to add it up. I would like to add up 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 to infinity. And you might think, well, if you're adding infinite things, aren't you going to get infinity? And the answer to that is no. Because this is very much the same problem that they've been that the ancient Greeks were fighting with philosophically, and it's become known as Zeno's paradox. And the reason we call it Zeno's paradox is because imagine you have a distance, say a distance from you, this is you. You've lost some weight, look at that, you're a stick. The distance between you and a door. Well, say that that distance is measured out to be 2 meters. Well, you could say, let's look at this distance in pieces. And halfway would, of course, be 1 meter. And then you could take half of that distance, which would be 1/2 meter. Then you could take 1/2 of that distance, which would be 1/4. And logically, you could keep cutting this distance up into an infinite number of fractions. In fact, it would be this infinity, this infinite addition. And you could say, well, how do we ever make it to the door? But of course, it's very easy to walk across a room for 2 meters and open a door. So the paradox being, it seems like it should be impossible to get to the door because there's an infinite amount of fractions between me and the door. But some of you learned that there's a nice little formula. Remember this? The sum of an infinite sequence, if it's geometric, is 1 over, or sorry, I guess I should say T1, term 1, over 1 minus r, where r is what we call the common ratio. And in this case, the common ratio, to get from one term to the next, all I'm doing is multiplying by 1/2. And the first term is 1. So this is 1 over 1 minus 1/2, which is 1 divided by 1/2, which is 2, which makes sense. All of these fractions actually do add up to the distance 2 meters. And that was kind of your first taste in grade 11 math of dealing with an infinite amount of things that actually do what we call this is converge. Remember that word? To a value. So keeping that kind of logic in mind will be helpful as we move into our new lesson today. And our new lesson today is what happens when we start approaching infinity with our limits. So first one is evaluate 1 over x as x tends to infinity. Now remember what a 1 over x graph looks like. Well, it goes through 1, 1, and it goes through -1, -1. But there's some symmetry to the way those two sides of the graph behave, but they look quite different. You see, if you start plugging in 1/2, you get 2. If you plug in 1/3, you get 3. If you plug in 1/4, you get 4. So you get this arm that does that. Right? If you plug in 2, you get 1/2. If you plug in 3, you get 1/3. And of course, you get a mirror image this way. Pretend that's a mirror image. Now, normally, we'd try some sort of algebra trick to get rid of this x in the denominator, but you know, that's normally what we do when we're heading towards 0. We're not heading towards 0. We're getting infinitely bigger numbers plugged in for x. So really, what we're getting is 1 over infinity. But of course, I'm going to write this in words, infinity isn't really a number. And it's certainly not a number you can divide by. But let's just think about it logically. Recall that this symbol itself says what? It means x approaches infinity. It doesn't say that I'm actually going to land somewhere in the number line and say, oh, I'm at infinity now. I'm just going to keep on going towards infinity. So the x number gets bigger and bigger and bigger. So you can conclude that 1 over x, as x approaches infinity, approaches 0. Because think about it as a series of fractions, right? Think about it as 1/2, 1/3, 1/4, 1/5, 1/billionth. Notice I'm heading towards 0, right? The fractions are getting smaller and smaller and smaller forever. And that's kind of what the graph is showing me too, right? As x gets bigger and bigger and bigger, what is the actual arm doing? It's getting closer and closer and closer to the x-axis, but it won't actually touch it, right? It is approaching 0. But of course, we've also had this conversation. We say in math that when we're approaching a number, we are that number, right? Remember, one of the first things we talked about in this course is that 0.9 repeating is in fact 1. We showed you a few ways that we can kind of logically say that that has to be true. So approaching 0 is in fact equal to 0. So I would say that even though it's weird, I'm dividing by something that's not even really a number, I can say that this limit does exist. It's 0. And my graph kind of backs that up, right? I am, oops, oh, I only wanted to erase the highlighting there. There we go. As I go further and further this way, I'm getting infinitely close to 0, so I am 0. Okay? So let's take a look at some of the other things we can do if we start thinking about approaching 0. Approaching infinity. Approaching infinity. Look at example 2. Let me make this bigger so you can see it maybe a little better. I don't think I need to write off to the side anymore. There we go. Let's evaluate this guy. The limit as x approaches infinity of x squared minus x over 2x squared plus 1. Now, if you've never seen one of these types of graphs, and chances are you probably haven't, it's a strange one. It is something kind of looking like this, actually. I'll try my best to make as good a sketch of it as I can. It does something like this, and then it kind of goes, down and up and that. Something like that, actually. I'll show it to you on Desmos in a minute. It'll do a better job of this than I will. But obviously, we can't just, if we plug infinity into the top and bottom the way it is right now, I'm going to get infinity over infinity, right? Because what's infinity squared? Infinity. What's infinity minus infinity? Infinity. Especially since this infinity's squared, right? It's double the infinity of the other one. And yes, in mathematics, we have to consider that some infinities are bigger than others. Just like that terrible young adult fiction book says. Some infinities are bigger than others. That's the one about the kid with cancer, right? I forget what it's. What's that book called? The Fault in Our Stars. Thank you. That's the one. Yeah. It's a terrible, tragic book, but you know, it's young adult fiction, so it's going to be tragic, right? Shakespeare must read young adult fiction and say, man, that is depressing. All right, so some infinities are bigger than others, and sometimes we can do algebra tricks to avoid them. So here's our algebra trick for this one. We are going to use our old friend, the 1 property. Remember that you don't change the value of an expression if you multiply it or divide it by 1. So here's what my 1's going to look like on this one. Can you see that? Sorry if I'm writing too small. That's my 1. basically, in words, what I'm going to say here is I'm going to divide the numerator and denominator by the largest degree of the variable in the expression. So I look at the expression and I notice, aha, it's got an x squared here and an x squared there. So that's why I decided I was going to divide top and bottom by those x squareds. That is my trick, that is my method, and look what that's going to do. It's going to mean that we actually don't head to infinity, because look at the graph. The graph, you might think, well, it's going up, maybe it's just going to infinity slowly. Actually, it isn't. It is not heading to infinity. This is not, this end, I'm pointing and you probably can't see me point. This end here is not going to go up forever. It's actually headed towards a horizontal asymptote. Remember the word asymptote? There is a horizontal line that it will not cross as it goes to the right. And this method is going to help me find it. So let's see if we can find it. That's going to change this to the limit as x approaches infinity of x squared over x squared minus x over x squared. Basically, I'm just distributing and multiplying. And then that's 2x squared over x squared plus 1 over x squared. Whoa. That looks like I just made it much uglier. But it's about to get a little better. Notice the x squareds cancel, so that's a 1. And x over x squared is 1 over x. And then the x squareds here cancel, so that's a 2. And then I can't do much with this thing, so it's going to just say 1 over x squared. Okay. Now remember, you can't divide by 0. But I don't have that problem right now. You can't really divide by infinity either, but I can pretend I'm dividing by infinity because I know 1 over infinity. 1 divided by a number that's infinitely big is going to be 0. So I'm actually going to plug in my infinity now. And just like before, once I plug in the value, I don't write that it's a limit anymore. I'm actually heading towards a value. And think about this. This value here is going to get infinitely small the bigger the number I plug into that bottom is, right? So it's not going to affect the 1. 1 minus anything infinitely small is still 1. So this numerator, oops, hang on. There we go. This numerator is a 1. And notice the denominator, this fraction is even smaller than the one on top. So 2 plus something infinitely small is still 2. And that, by the way, is what's happening up here. This thing is heading, come on, pen, there we go. Nope, this thing is heading towards the y value of 1/2. That value there is my limit. The limit exists. I guess I could have maybe done one more line in here. It's 1 minus 0 over 2 plus 0. Right? These things here are, mathematically speaking, these things here, come on, pen, these things here are mathematically 0. Okay? All right, let me show you what that looks like in Desmos, just to show you that I didn't make this up. Oh, I haven't opened Desmos yet today. Hang on. Let me get the thing out here. There we go. And Desmos, I graphed these the other day and I saved them. I don't have high hopes that my video is going to work because look at how slow this is. All right, let's see. Desmos, come on, Desmos. While Desmos is thinking about opening, I should check to see, are we Yeah, encoding overloaded. I don't know if my video is going to work or not. Oh well, we'll find out. Okay, so back to Desmos, and I saved a graph here. Limits to infinity. Let's open it. And there we go. So there's the, oops, let's get rid of that. So there's the first thing I graphed today, y equals 1 over x. And as you can see, yeah, you were definitely heading towards 0. The further right you go, you're getting closer and closer to 0. You're definitely heading towards 0. Here's the one we just did. As you can see, this thing is heading towards 1/2. It is never going to cross it. It is heading towards 1/2. Good morning. Okay, so there we go. Now, you might be thinking, wait a minute, it crosses 1/2 over here. Look, see, I can actually see it crosses 1/2. I got a little bit of space there. Yeah, that's one thing about horizontal asymptotes. Horizontal asymptotes don't necessarily have to be for the entire function's graph. It can only be for part of it. And in this case, this 1/2 is a horizontal asymptote only on the positive side of the graph. On the negative side, it does cross it. Interestingly enough, though, once it crosses it, it doesn't touch it again. Notice it's actually also heading towards 1/2 as you go to the left, which is interesting. And we'll talk about that in a minute on the next example, or a couple examples from now. Okay, let's go back to the notes. Okay, this is an important thing to kind of keep in mind. The limit as x approaches infinity of -1 to some power does not exist because when x is even, well, then you could say that, of course, whoops, there I am on the highlighter again. Oops. There we go. And when x is even, -1 to an even number, of course, just makes 1. But when x is odd, -1 to an odd power is, of course, -1. So the graph for this thing is going to look quite strange. Of course, 0 is even, so I'd get 1. And then, of course, at 1, I'd get my -1. And then at 2, I'd get this. So I'm going to get something like that. But what about fractions? Well, fractions can be odd or even too, right? -1 to the power of 1/2 does not exist, right? Because you can't square root a negative. But -1 to the power of 1/3 is just -1. So you end up kind of with this infinite series of points that either exist or don't exist. This is maybe the ultimate in not continuous graphs. Even Desmos has a hard time graphing this one. If I go back to Desmos to talk about this one, it tries, it does its darndest. You got to give it credit. It gives it the old college try. But come on back to the home there. Can you see that even? There's these little dots. I don't even know if you can. Oh, that just makes them go away. It gives up. If you go to a bigger scale, it really gives up. Or I guess a smaller scale. Yeah, same thing the other way. It does try, but it just gives you this series of dots because it can't exist everywhere. There's a whole lot. There's infinitely as many places it doesn't exist as there is places where it does exist. So we can't in any way say that we're heading towards a value. We can't say that we have a limit. You could say maybe that the limit approaches two different values infinitely. You could say that the limit as x approaches infinity of -1 to the x is equal to either 1 or -1. But since it can't be defined, but is not definable. I'm not sure if that's how you spell definable, but good enough. All right, another note. What about just the limit as x approaches infinity of x? Well, you would also say that that doesn't exist either, because the y value approaches infinity, right? If you graph y equals x, here's one that I won't bother showing you on Desmos. It's the simplest graph we can get, and I drew it as a curve. Hang on, let me undo that. Let me make that straighter. There we go. Let's try to make this straight. Close enough. So this is, of course, y equals x, and notice as x approaches infinity, well, then y is going to approach infinity as well. So the limit to exist has to approach a specific value, and infinity is not one of them. So you would say that the limit as x approaches infinity of x does not exist. But you could say that even though it doesn't exist as a value, you'd say no value exists. You still understand that there's a behavior to its graph. You still understand what the numbers are doing. The limit is approaching infinity from the positive side. It's approaching positive infinity. Actually, now that I think about it, I should put that positive in front of the infinity. It's not approaching it from the right, it's approaching it as positive infinity. Come on, eraser. Let's try that again. And limit is approaching positive infinity. Notice that if I was saying, well, what happens as you go this way forever, to the left? Well, then you would say that once again, it doesn't exist, but I know that the limit is approaching negative infinity. And that's kind of the new wrinkle for this part of the chapter. We can't just throw up our hands and say, the limit doesn't exist. I know it doesn't exist. We have to be a little more descriptive than that. We know it doesn't exist because it's not getting to be a value, but is it heading towards positive infinity or negative infinity? Some sources would say that the limit of this, of course, is plus infinity, and the limit of this is negative infinity. And some textbooks would just say does not exist. It depends what the textbook's asking you for. If a question says, if the limit does not exist, say does not exist, then just say D and E and you're done. But the questions we're going to ask, I can guarantee you your next test will say this later this week, is it's going to say, if the limit does not exist, determine if it's heading towards positive or negative infinity. So you're going to want answers like that. All right, this guy should look familiar. Look at example 3a. Think about this. As a geometric series, right? As x gets bigger and bigger, when x is 0, of course, you get 1. As x is 1, you get a half, and then you get a quarter, you get an eighth, you get a 16th. What is the trend on these numbers? Clearly, you are heading towards, you're heading towards 0. So is that just something I can memorize then? All fractions have to behave that way? Well, take a look at the one on the right. What's the geoseries for this one? Well, if x was 1, we'll start at 1 for this one. If x was 1, you get 5/3. If x is 2, you get 25/9. If x is 3, you'd get 125/27. If x is 4, you get 625/81. And I don't know if you can tell this or not, but all those fractions are getting bigger. Right? 5/3 is 1 2/3. 9 goes into 25 almost 3 times. 27 goes into 125 like over 4 times. So clearly these numbers are getting bigger. So I would have to say that the limit as x approaches infinity of this fraction to the power of x does not exist. But even though I can't say it exists, I can't say it reaches a number because it's just going bigger forever, I can say it is trending to positive infinity. All right, which brings us to example 4, our last example for today. All right, If I plugged the number into it right now, I'd get infinity over infinity, which doesn't tell me anything. So I'm going to use my new technique. I'm going to multiply the top and the bottom by 1 over x squared, which of course is going to look like this. And that's going to give me the limit as x approaches infinity of 4x squared over x squared divided by 3x over x squared plus 2 over x squared, which is equal to the limit as x approaches infinity of 4 over, all right, that's going to end up being 3 over x plus 2 over x squared. Well, again, when I plug in infinity, those things, of course, are heading towards 0. Oops. Ah, yeah, okay, I'll do this in 2 steps. Hang on. Infinity plus 2 over infinity squared. And so, yeah, this thing is, of course, just heading towards that. Which means, of course, you can't divide by 0, so therefore it does not exist. But which way is it going? It does not exist, but it's definitely heading towards positive infinity. It's going to go up forever. Now, how can I tell that? Well, because notice these numbers here are my limit numbers, but I know that they are, in fact, just numbers that are getting smaller and smaller and smaller. And 4 divided by a smaller and smaller and smaller number is just going to get bigger and bigger and bigger forever, right? At some point, maybe you were even somebody tried to convince you that a number divided by 0 is infinity. That's not true. A number divided by 0 doesn't exist. But a number divided by something that's approaching infinity, you can say is approaching 0, getting closer and closer to 0, you can say is getting closer and closer to being infinitely big. Now, what if instead of that, what if the question was, maybe add to this here, I hope you have a little bit more room. What if it was negative infinity? So the difference being, what's this thing doing as we head forever to the left on the graph? And as you can see here, well, I don't have to go through the logic again. I'm still going to get to this place. I'm going to get to here after I've done the same algebra trick I did on the first one. Now think about this logically. What's happening in that denominator? Well, this term here, this negative value is getting infinitely big. It's blowing up, but it's always negative. And what happens when you square a negative? You get a positive, right? So I might as well just rewrite this as 4 over 3 negative infinity plus 2 over positive infinity squared. Now, start even thinking about numbers. Like what happens when I have the number 1 and I'm going to plug that in. So this is, no, 1's too small a number. Remember, this is heading towards infinity. Let's think about 100. If you put 100 in this denominator here and then you square it, well, now you've got 2 10,000ths, right? And if you put 100 here, you've got negative 300ths. Notice this is always going to have more value than this because this one's racing towards, I'm going to put this in words, heads towards 0, I'll say faster than that one. Heads towards 0 faster, but is positive. This one heads towards 0 as well, but is negative. So I'm going to say that this is going to equal 4 over 0, but we're approaching 0 as a negative. Right? This denominator, no matter how big the number is you put down here, has to be a negative number. So therefore, it does not exist, same as the above one, but it's heading towards negative infinity, not positive infinity. And I'll give you a second to finish catching up to my notes, and then let's look at it on Desmos. If I'm right, the end behavior of this thing is when x is going to the right, the graph should be going up forever. And if x is going to the left, it should be going down forever. That's what our limits are telling me here. Can you see why this denominator, when I'm heading to the left, has to be negative? Think about the fractions that are involved there. And the one on the left would be more negative than the positive one on the right is positive. All right, let's take a look at it in Desmos. It's a strange looking graph. These are interesting creatures. They have something called oblique asymptotes, which basically means they have diagonal line asymptotes. Yeah, there we go, these guys. As I go to the right, I am definitely, there we go, come on. Oh, it won't let me do that. As I go to the right, I'm going up forever. As I go to the left, I'm going down forever. And this thing does have an asymptote that is diagonal. There used to be a time when the grade 12 course actually looked at diagonal asymptotes. We'll talk about it a little bit when we get to curve sketching. Okay, so there we go. So that's today's lesson. I'm going to stop my video. Kind of doubt that it worked. Oh, jeez. Sorry. But we'll stop it anyway. Oh, the error message went away. Oh, no, there it is. Encoding overloaded. Oh, well. We'll see if it worked. If it didn't, I'll record it later. Oh, I didn't mean to do that. Nope.